I've got. The biggest thing that we need to remember is really kind of what's happening at the bottom end of this. Pretty much the only true aspects of Dalton's theory. That when we're making compounds, we can take different atoms, we get small whole number ratios, and we can generate differing types of compounds out of it. Okay, so those are the big kind of conclusions that we want to find with those. So let's take a look at a chemical reaction. Solid sodium hydride reacts with acetic acid to produce aqueous sodium acetate and hydrogen gas. So for this next exam coming up next Wednesday, I believe, you are responsible for being able to come up with a chemical reaction for that. So go ahead and try that. If you got questions on where to start or what things to miss, or you just want me to look at it, raise your hand, I'll come to you. But get something down. At this. So, a couple things that pop up. Number one, you have to know the name of all your elements. If you don't know that, you need to know that very, very quickly. Right? Because the exam is next week, right? So you need to know that. So let's start it off with solid sodium hydride. I would argue where we should be starting is with the sodium. And our symbol for sodium is Na. Our symbol for hydride? That one's a little bit weird. Okay, you're saying H negative. Okay, it is sodium next to hydrogen, so we should have picked up at least NaH. The part that becomes tricky would be balancing that out, and we'll look at that in just a second. Hydride came second. That's why we changed the suffix from hydrogen to hydride. Okay? We know it's just hydrogen by itself because we see the letter D. And that letter D is a signal that what we're looking at is a solo element. We're looking at a binary ionic compound, okay? Not, say, a polyatomic ion. How do we know we had a polyatomic ion? Instead of that being a T, we would, or give that away. Instead of that being a D as in dog, we would see T as in tango. That works, right? Okay. So we know we're looking at the single element. We could also go through, because we've got it here, it says the phase, and we could add our solid. Before we continue on, though, we should make sure our formula is actually balanced. That means evaluating the charge on each of those pieces. What is the charge from sodium? A +1. I would recommend you write underneath for the charge on it, because if you write it up next to the sodium, it then starts to imply that that formula has charge. That formula cannot have charge because it's a compound. Okay? So we're showing our work down below. We know that if we add this all together, that this has to equal 0 for the overall charge. Okay? So what is the charge from hydride? That becomes a little bit trickier. Hydrogen, if we remember its charge, it being in group 1, should suggest that it should be a +1 charge. And it's +1 to look like what? So remember, our charges come from trying to look like a noble gas. Hydrogen's losing an electron to become a +1. What noble gas does it look like? It looks like the fictitious noble gas that's above helium. There isn't one there. So we've removed all electrons. It's roughly equivalent to a fictitious noble gas. But remember, we have another option. Instead of losing an electron, I could have gained an electron for hydrogen to become helium. So there are two charge states for hydrogen. One is positive, which is the more common one. The other one is negative. Okay. Somehow or another, I have to figure out how many sodiums I need and how many hydrides I need to balance that out. Anybody know the answer? One of each. Okay, we could go through as we talked about in the video for nomenclature and say x was 1 as a guess, right? We'd get 1 plus negative y equals 0. We get 1 minus y equals 0. We get 1 equals y. Everybody remember that? painful, long work, but you just looked at it and said, well, if it's just one, it solves. Okay?
Work equals points.
Unfortunately not, for the sake of nomenclature. Okay, so we now have sodium hydride solid. What does reacts with mean? Plus. Okay, acetic acid. So the first thing you should be saying, as soon as you see acid, you should be writing H and you're right, but not for what I'm talking about. As soon as you see acid, you should be saying H and aqueous. We have phase information specified on it. Okay, that's what you guys have learned to this point. The rest of it is dealing with the acetic part. Okay. Do we know if this is a binary or a ternary acid?
Ternary.
How do you know it's ternary?
By the ending IC.
Nope. The ending IC is used in both binary and ternary acids. In a binary acid, the name will always start with hydro. Is hydro written next to acetic acid?
No.
No. That means by definition is a ternary acid, which means the name of the acid is dependent on the name of the complex ion. Okay? Which is our acete. Let's just say that. Okay? Because we have the ick now, you can say that we ended with 8, because I ate too much and I got ick. And I'm now looking at the acetate ion, which has what formula? Now you can give it to me. C2H3O2. Okay, because I wrote too big, it says then to produce. What does that mean? A reaction arrow to produce what? I have sodium, acetate. Well, acetate's the complex ion, C2H3O2. Okay. The phase said it was aqueous. Is that formula correct? What is the charge on sodium? A plus what for sodium? A plus 1. We know that because sodium's a group 1 metal. We looked at the periodic table. Acetate has what charge? A minus 1. How do we know acetate has a minus 1 charge? That is one you have to memorize. You don't have a choice. You have to have that one memorized. Right? So is your formula correct for sodium acetate?
Sure.
Yes. Then what do we follow with? And plus sign. Hydrogen gas. What symbol are we going to write? H, and we can even write a phase. Okay, so we've got Hg. Unfortunately, we'd be wrong for that last one. What is the symbol for hydrogen gas?
H2.
It is H2. How do we know it's H2? Something that we would memorize. There are certain elements on the periodic table that when they are all by themselves in their elemental state, they are diatomic. Right? Which means they have to be partnered. Hydrogen is one of those elements. Right? In a phrase that we'll learn here shortly, it's H for have, meaning I need 2 hydrogens. So I end up with H2. And what I've now done is written out the equation. To formalize this, I should go through and check and make sure everything is balanced. How do I check to make sure things are balanced? What's that? Math, that's kind of a vague answer. We go through and you look at each and every single element and you compare on each side of the equation. Do they match up? Do we total to the same amount? How many sodiums do we have on top? 1. How many sodiums do we have on the bottom? 1. Sodiums are balanced. How many hydrogens do we have on top? 5. Yes, we have the hydrogen from our acetic acid, and yes, we have the hydrogen from the hydride, but we also have 3 hydrogens from the acetate. And we have 5 hydrogens on top. How many on the bottom? 5. How many oxygens on top?
2.
Oxygens on the bottom? 2. Is everything balanced? Yep, we can now walk away and say we've solved the question. Okay? So lots of little pieces that go into this. You're responsible for every single aspect of that. So when you think back to nomenclature, you go, oh God, I never have to worry about that again. Yes, you do. Okay? Not only do you have to worry about it in putting together your compounds and your structures, you will have to worry about it in the calculation and the thought process behind how we balance things out. Okay? Which you should be aware of because you all watched that oxidation state video that reiterates those exact same thoughts. Okay? So back to our hydrogen being H2. There are 7 elements on the periodic table that are diatomic in their elemental state. You're required to know those 7. There's very few mnemonic devices that I have ever memorized. Okay? The 2 that I can say off the top of my head that I have memorized is the Leo says gur, which you're aware of because of that video, and have no fear of ice cold beer. Okay? The Leo says gur was, well, because that's my astrological sign, so that then stuck in my head. And then I learned this one probably in high school and was like, haha, beer. Okay? And now that one stuck in my head. Okay? That's the extent of my ability to memorize mnemonic devices. Okay? If you're having trouble with the complex ions, the Tutoring Center has tons of little mnemonic devices that are fantastic about camels and tents and walls and stuff like that. Okay? And it works. Okay? But I can't memorize those. Those don't stick. Okay? So how does this one work? Have no fear of ice cold beer. The first letter matches up. Hydrogen, have, nitrogen, no, fluorine, fear, oxygen of, iodine, ice, chlorine, cold, bromine, beer. Okay? Yes, there are multiple symbols that begin with C, and there's multiple symbols that begin with B. Okay? You kind of have to do your best to figure that out. Make sense? Okay. Because there are other devices behind this, we'll go through and mention a couple other things. There are 7 of them. So if we go through and highlight them, oh, interesting. What symbol does that look like? Just highlighted it in red. That looks like a 7, except how many elements are boxed in? 6. 6 does not equal 7. Oh, that's right, because I forgot one. So if I can remember 7, there you go. Okay. There was a tutor that apparently liked hockey and played hockey a whole lot, and he saw something else here. What did he see? We've got a hockey stick and the puck. Okay. Any way you remember those elements is good. You need to know those as diatomic. When they show up by themselves, you have to specify them, okay, as diatomic as 2 elements. Make sense? Okay. So, balancing chemical reactions. How much have you guys been practicing your balancing? How many people even know what balancing a chemical reaction is about? Okay. Let's reiterate when the test is. The test would be next Wednesday that covers balancing reactions. Everything since last test and last test. Okay? All tests are cumulative. Okay, so we need to be able to balance things. We have to have the same thing on both sides of the equation. This goes back to the conservation of matter. We can't create or destroy energy. We can't create or destroy matter. So everything must balance out. That does not mean the exact same species have to show up on both sides. Okay? It means the exact same elements have to show up on both sides. So I can go through and change where those atoms are connected, but I can't get rid of the atoms. Kind of make sense? Okay. As far as rules on how you could go through and do this, these are the guidelines for balancing equations that I would recommend. Okay. The most important one seems to be the one students don't like doing. So let's go ahead and highlight that one. Right there at the bottom is check your work. Okay. Remember how every so often I come up with rules and I say I want you to follow these rules until you are irritated that I made you do that and you're mad at me? Okay. This is one of those rules. When you're balancing equations, you need to leave the test being, I got every single one of those right, or I got every single one of those wrong. There's no, I think I got balancing right. There isn't. Because you go back and check your work. It either adds up or it doesn't. If it doesn't, you're just guessing. You might as well just accept that you got it wrong. Okay? So, balancing takes time. There's lots of steps and lots of integral pieces behind it. It may be something that's worth saving for the end of the test. Okay? Unless you think you're really a rock star at balancing, then by all means jump straight into it. Okay? But it takes time to go through and do these. Okay? The biggest part is that checking of your work. Okay? So I completely forgot to mark which ones I did in the video. I don't think I did them all, but I would bet I did that first one, maybe the second one, and this one. That's right. But I didn't do the middle one? Or did I do that one? Oh, I couldn't have done the middle one. Did I show you that one?
No, you made us do it on our own.
I made you do it on your own. Okay, so let's see. How well did you do on your own? How many people got the answer right? How many people got the answer wrong? How many people have a lot of work to do before Wednesday? Because you aren't even raising your hands. Yeah. Okay. You need to go back and review. So let's take a look at balancing the equation on how we would process this. Okay. Element by element. I would write down the symbol underneath the arrow because I want to go left-hand side being the reactants and right-hand side being the products. How many aluminums on the left-hand side of the equation? Okay, well, aluminum only shows up once. It's got a subscript 2 next to it. That 2 means I have 2 aluminums. Move to the right-hand side. How many aluminums do I have? Well, there's a 3 here.
But it's for, no, it's for the whole thing.
What is that subscript 3 for? That applies to, the subscript always applies to what's directly in front of it. What is directly in front of it? Parentheses are directly in front of it. That 3 applies only to the parentheses. Is aluminum within those parentheses? No, which means?
It doesn't use it for.
The 3 has nothing to do with the aluminum. So how many aluminums are on the right-hand side? There's only 1 specified. Is that equation balanced?
No.
No. I have to have the same number of each element. So the aluminum isn't balanced. I now need to fix this. And I can fix this by changing the coefficients on the equation. Okay, the coefficient would be the number in front. I need 2 aluminums. How do I make sure I have 2 aluminums?
I think 2 in front of it.
Put 2 in front. And this now becomes 2 aluminums on the right-hand side of the equation. Awesome. Aluminum is now balanced. Do I stop and go on? No. I got to move on to the next element. What's the next element I want to balance? Okay, I think I heard a sulfur. I'm going to regret doing this, but I'm going to go ahead and start it. Okay, how many sulfurs on the left-hand side of the equation?
3.
Okay, I heard a 4. I heard a 3. The 4 applies to what? Only what's directly in front of it, and what's directly in front of it is the oxygen. There is a 3. What does the 3 apply to?
Anything in parentheses.
It refers to the parentheses in front of it, which then means how many sulfurs? 3. The sulfur is within those parentheses, so I end up with 3 sulfurs. Make sense? How many on the right-hand side of the equation?
1.
Only shows up once. Is sulfur balanced? What do you need to do?
Change the coefficient.
Right? Now I got 3 sulfates, or 3 sulfurs.
But now you're oxygen.
Oxygen's not on my list, so I don't accept that as a valid complaint about why that's wrong. Okay. What did I just change by putting that subscript in? The chemical compound. Before we balance any question, we have to make sure the chemical compound is correct, because once we start balancing the equation, what can we do to the chemical compound? Rhymes with something. Nothing. You cannot change the chemical compound once you've started balancing the equation. By changing the subscript, we're now altering the compound. I can only change the coefficient in front. So I need to put a 3 here. I now have 3 sulfurs. Make sense? Okay. What's the next element I could try and balance? Okay, I heard an oxygen. I would make the argument, and this one's a solid argument actually, that I should not touch oxygen. Why? Doesn't oxygen balance itself out somehow? Kinda, sorta. Not always, but it does kind of work out where you don't have to stress about oxygen so much. Why would I leave oxygen alone?
Because it's already part of the compound.
Oxygen's already part of a compound, but so is sulfur. Look at the reactant side. How many times did aluminum and sulfur show up each? Once. On the product side? Once. Take a look at oxygen.
Twice in each 12.
Twice on each side. That means if we had to go through and balance the oxygen, we have 2 different places that we could change the coefficients. Is that going to make things really difficult to balance?
Yes.
Yeah, that'll probably make things awfully hellish. Which means don't touch the oxygen and hope that it works itself out at the end. Okay? So if any element shows up multiple times on any side of the equation, don't balance it first. Move to a different element. Okay? Oxygen typically shows up a lot because oxygen is insanely reactive. Okay? This is why we live, because oxygen is reactive. Okay? So let's leave oxygen alone for the moment and move on to the next element. I would argue there's a different element than nitrogen. I'd argue the barium is the first thing to pop up. How many bariums do we have on the left-hand side? 1. How many on the right-hand side?
3.
Is that balanced?
No.
What do you have to do?
Change the amount on the left side.
Change the coefficient to become a 3. Is our barium now balanced?
Yeah.
Yeah. Okay. Now what do we move to? Now we can move to our nitrogen. How many nitrogens on the left-hand side? This is going to be a fun one. There's 1 nitrogen within the parentheses, but then there's a 2, but then there's a 3.
Oh no.
So I'll end up with 6 nitrogens. We have to layer each of those. So start on the inside and slowly work your way out. So we have 6 nitrogens on the left-hand side. How many do we have on the right-hand side?
6.
Oh, you're totally right. Sorry, I missed that.
Magical. 6.
We have 1 within there. There's 3 within the parentheses. And I run that question or that equation twice. I get 6. What does that mean? The nitrogen's balanced. Okay. What does that leave me with? Oxygen left to balance, and of course I wrote everything massively huge, so let's try and rewrite that. While I'm rewriting that, you can go through and fix that. Oxygen, 6, 6. What was our barium? 3 and 3? Close enough. Oxygen, how many oxygens on the left-hand side? Is that getting a bit messy? You want to clean that up? Yeah, okay, so let's clean that equation up. Notice the thing I'm not erasing would be the coefficients, because we need those. Okay, so I get 4, but I have 3 of those, so I get 12. And the next one I have 3, but then I have 6, so I have...
But that equation's ran 3. Oh,
Whoop.
That's why it's 6.
No, you're right. I counted that wrong. That equation ran then 3 times, which then means 12 and 18.
30.
Okay. How about the left-hand side? We have 3 and 3, which is 9, but
Ran twice, so 18.
the next one I've got
Option to the
4, but
So
the
12
3,
times. So 12. So
12.
30. Remember
And what happened?
Option even out.
The oxygen evened itself out, so we didn't have to worry about it. Okay. Now what do?
Check our work.
We go back and we check our work. Yay, checking our work. And of course, because I got an eraser, I can go through and erase everything, except the stuff that's important.
Like half of it. And one of the aluminums.
How many aluminums do we have on the left-hand side?
I don't know.
2. And the right hand? 2. How many sulfurs on the left-hand side? 3. And 3. How many bariums? 3. And 3. How many nitrogens? 6. And 6. How many oxygens? 30 and 30. I think you did that math too fast, so guess what I'm going to have you do?
Again.
Check it again. No, seriously, check it again. I want to see all the work written down. If I don't think you're writing stuff down, I'm going to turn it into a quiz that I will grade super strictly. You don't even need to write out the equation. You can just give me an arrow and then write the elements underneath. Start showing the balanced work out. Because you have to do multiplication, all that kind of fun stuff, show that addition. You can't just say those numbers again. Right? All the stupid oxygens, multiple different places. It'd be ideal if we had a different way to do this. So a couple people asked, couldn't I have just balanced the sulfate on both sides instead of breaking it down into the individual elements? Well, did sulfate stay sulfate through the course of the reaction? Yeah. So guess what you could do? Balance sulfate. Okay. We don't have to break it down into the individual elements. We can balance the complex ions as long as the complex ion does not change its identity. If it somehow changes through the course of the reaction, then you cannot balance the complex ion. Okay? So in this case, sulfates. How many sulfates on the left-hand side of the equation? All I have to write is 3. On the right-hand side, it's 3. Not 12. Where did 12 come from?
Oxygen. 3 times 4.
You're seeing the 4 and multiplying that through. That 4 is as much of the identity of sulfate as A is part of barium. Okay, so we can't multiply that 4 through. How many bariums are there on the left-hand side? 3. Right-hand side? Nitrates? Yes, there's 2, but then... And right-hand side?
6.
And I get 6.
I like that better.
Does it balance? Yeah. Which do you prefer? All honesty, I don't really care. Do it and do it right. Show your work, I'm fine with it either way. I tend to prefer the complex ions because I don't have to count as high, particularly when it comes to oxygen. Whoa, don't do that. Take a look at this last one. Can I balance this one using just hydrogen and carbonate?
No, it changes.
Why not?
Because it changes.
Carbonate, CO3, does not show up on the product side. I get CO2. Is CO2 carbonate?
No.
No. So I cannot balance this as hydrogen and carbonate. I will have to balance it out as the individual elements. Do you guys want to go through and attempt it? Check your work and all that fun stuff?
Sure, why not?
Sure, why not? Go ahead and start it, and I will answer some questions. 2. How many hydrogens on the right-hand side? What's the next one? Carbon. Carbon's on the left-hand side. 1. Carbon's on the right? 1. Oxygen's on the right. I only see 2.
There's one in the H2O.
Remember, oxygen's tricky because it can show up in multiple locations. We have to add wherever it shows up. So there are 3 oxygens on the right-hand side. On the left, 3. Is this equation balanced? Yes. Exam question, what is the sum of the coefficients of the balanced equation? Right. So let's write down some multiple choice answers here. This is a pretty boring one, unfortunately. Let's say 0.
1.
Let's say 1. Why not? 2, 3.
So D.
And goats for the heck of
What's
it.
with you and goats?
I don't know.
There's like 800 quiz questions. with
I
goats.
want a goat, actually. Goats are kind of cool.
They're quite expensive.
Beside the point, where did the 0 come from? Because I heard a couple people say 0.
Because there's no.
There's nothing written there, right? So it should be a 0 coefficient. Wrong.
0 times anything.
If that was a 0 there, then that thing disappears from the equation. Okay? 0 times anything is 0. So if I put a 0 in front of the water, what does that mean as far as the amount of water? There is none. So what is implied in front of each of those? A 1, which means the sum of our coefficients? 3. The answer is D. Where did answer B come from?
Bad math.
The coefficient on the reactant side is 1. Where does C come from? Sum of the coefficients on the product side is 2. Okay? All your numbers, don't ask about goats. All your numbers will show up somehow in the multiple choice answers. So don't just be like, oh, numerology says if the number shows up and I got a number that they must be right. Okay? I write tests better than that most of the time. Okay? You actually hope I don't write tests better than that. So classifying our chemical reactions, you are responsible for being able to look at a general reaction equation and be like, boom, that is single replacement. Once you know what type of reaction it is, you then have extra rules to follow along. Because you've seen these before within the video, are there any of these that you need to kind of earmark or star as being more important or relevant for, say, a test?
Composition and double replacement.
Double replacement, I would argue, should be starred. Single replacement should be starred, and neutralization should be starred. Why should all 3 of those be starred?
They're fancy.
You're required to predict products.
Oh.
You are not required to predict the products of a combination or a decomposition. In the homework, you may expect, the textbook may ask you to do that, okay? But the textbook knows that you have the textbook in front of you. Use it. Okay?
Combustion.
Combustion, unfortunately, isn't on my list. That needs to get added. Okay. And you also have to predict products on that one. I want to add another layer of stars. Single replacement and double replacement need to get further starred. Why would they get further starred?
Because they get confused often.
Hopefully not. You need to decide if there is a reaction. How do you know there is a reaction for a double replacement? How do you know there's a chemical reaction, period? Change in identity. But if you wrote out your equations, it's always going to look like the identity changed. Change in phase. Right? Change in color. Change in energy. All those chemical changes, right? Those are signifiers for a chemical reaction. When we look at these equations, do those stand out? Do we see a place to write change in temperature? No. So that doesn't help us. Do we see a place to write change in color? No. So that doesn't help us. What does help us? Change in phase, because where's the phase information always supplied? It should be supplied as a subscript next to every single thing. I'm just writing P for phase. So what you would have to go through and do is say, did I get a new phase? If a new phase has happened, I have a chemical reaction, that reaction occurred. Single replacements become a little bit trickier, so I would actually add another star on top of that. What's the star there? Not quite. Okay, I know what you're trying to get at there. Single replacements become extra starred because of the activity series. You have to be able to rank the atoms and decide should a reaction occur, okay, based off of the activity series. Because if we just write out a single replacement reaction, we will see a change in phase every single time. Okay? So what we have to decide is that change in phase valid? That comes back to interpreting the activity series. Okay? If we want to get extra irritating on that, we can add another star to the single replacements, because the single replacements are your standard example of what type of chemical reaction? Redox, reduction and oxidation, which means we're changing the oxidation state, which was the video you watched this weekend. Okay? So we have to be able to acknowledge how the oxidation state changed. So the single replacement reactions have a lot of stuff kind of running against them as far as you're concerned for what you have to memorize. Okay? So, nope, we're not doing that. Do you guys want to go through and classify some more real quickly? Yes. Saw a head shake, yes. I forget which ones we did. Pretty sure we did the first one, so let's get rid of that one. Pretty sure we did the second, so let's get rid of that one. Yeah, we did that one too. How about that one? How would we go through to figure this out? Step 1. What's that?
Write it all out.
What do you mean write it all out? I agree. Clarify.
Write its symbols and
Put down the symbols. Sodium, Na, chloride, Cl. This is aqueous. Is that the proper formula for sodium chloride? How do you know that?
memorize.
You're not supposed to memorize the formula of sodium chloride. You may have, but you're not supposed to memorize it. How do we know that's correct?
We check
You are required to memorize the charge on sodium is a +1. You are required to memorize that chloride is a -1. 1 and 1 of each neutralizes the charge. That is a correct formula. Reacts with aqueous lithium nitrate. So reacts, we've got a plus sign. Lithium nitrate, Li. What is nitrate? NO3. How do you know nitrate was NO3? You are required to memorize that. There's 7, some number that you're required to memorize that is starred in the nomenclature video. That's why you need to watch that video. Is that the proper formula for lithium nitrate? How do we know? Charge on lithium. Lithium's a group 1 metal, making it +1. Charge on nitrate? -1. We know it's a -1 because you are required to memorize that. You have to know the charge on your polyatomic ions. Is that formula balanced? Yes. Okay. Which sets us up with the next part. We're saying those two react. We could go through and predict products, but to predict products, we should know something about what type of reaction we're looking at. Okay. If we go through and look at this, we've got a positively charged species, okay, or a cation with an anion, plus a cation with an anion. Which of our reactions took two things and combined them where we have cations and anions all the way through? The double replacement. Now that I know it's a double replacement reaction, I can run the exchange. Sodium needs to be combined with nitrate. Lithium needs to be combined with chloride. Before I do anything else, I now have to verify, did I draw the correct formulas? What is the charge on sodium? Plus 1. What is the charge on nitrate?
Negative 1.
-1. Is that formula correct?
Yes.
Yes. Lithium charges?
Plus 1.
+1. Chloride?
-1.
Did I draw that one correct? Yes. Last part that I need to do for a double replacement, because I'm required to predict if the reaction occurred, I need to know the phases. How do we know the phases? I think this was in the video, but I'm not positive. It's an old video now, 2 weeks ago. You would need to know your solubility rules, which we will look at hopefully later today. And what we end up finding out, according to solubility rule number 1, both of these are aqueous. This is a double replacement reaction. We've predicted products. Should this reaction occur? No. What do you mean? Why not? Didn't I just draw products?
There's no phase change.
There is no phase change. Everything is aqueous. No phase change means no chemical reaction occurs. Okay? Lots of steps to be able to get to a final answer. Make sense? Okay. Did we do the zinc and lead sulfate last time? Yeah? Okay, well then we'll have to do that. Take a look at that last one. Do everything you can on it. Okay? Yeah, that's intentionally vague. But label everything you can possibly do. Type of reaction. What are the products? Should the reaction occur? Balance it. So where should we start? First thing you need to identify is what is the reaction. If you don't know what the reaction type is, you're done. Okay? So our first place is the reaction type. What type of reaction is it? Single replacement. This goes back to recognizing the patterns. We have a single element with a 2-compound or a 2-piece compound. We're looking at a single replacement reaction. Once I've identified it's a single replacement reaction, what can I do? I can do the single replacement. Okay? Gold is what kind of an element? A metal. Copper? Sulfate? Non-metal complex ion. Which of those things are the same?
Metals.
The metals. What should we be doing the single replacement of?
Metals.
The metals. And we end up with copper plus gold sulfate. So far, so good? Okay. The state of copper. So when we're running the single replacement reaction, we are doing a full replacement here. What is the charge on our gold to start? Where is the charge specified?
No.
It is always specified, so you can't tell me nowhere. In the upper right-hand corner. Look at the upper right-hand corner of our gold. What is written there? Nothing. What is our mathematical symbol for nothing?
1.
I know, we're flipping on it from balancing equations. 0. What is the charge of gold on our reactant side?
0.
0. Which means what happens to the copper? If we're doing a full single replacement, the copper had better be what charge on the product side? 0. Okay, and if we want to get specific, we can go through and show that charge so that we know that it's 0. Okay, what is the charge on gold on the product side?
3.
That's a much harder question. Okay. Typically, we could determine the charge if we had the proper formula. Do we have the proper formula? We don't know. We're just guessing. We just did the single replacement, and it would balance out if we knew what all the charges were. So how do we predict the proper formula? You have to be given more information, like the top of the page, where it says gold is typically a +3 charge, which means we can now add our information into this. We have a +3 from our gold. What is the charge on sulfate? A -2. Would those charges balance appropriately? No. So we have to determine the amount of each of those. The overall charge must be equal to 0. It's now a question of, according to my method, guessing and checking until we have the right answer. Okay? You can pull the crossover method if you want, what the textbook talks about. That's where I'm just going to leave that, is you can do that if you would like. After you track out the work, what do we find? We need 2 golds and we need 3 sulfates. We now have the proper formula for our gold sulfate. What phase should it be? Aqueous. We're doing a single replacement. Let's just keep it simple and just do the full swap. Okay? Is this equation balanced? No. Nope. So what do we have to do? God, seriously? Yeah. Yeah, seriously. How many golds on the left-hand side? 1 on the right-hand side.
2.
Is it balanced?
No.
How do you fix it?
Change the coefficient.
Change your coefficient on the left-hand side. Copper. How many coppers on the left? 1 on the right.
1.
Is it balanced?
Yes.
Yep. Cool. Sulfate. I'm going to have to erase. I'm going to erase the copper. How many sulfates on the left-hand side?
1.
Sulfates on the right?
3.
3. Is it balanced?
No.
No. So what do we do?
Change the coefficient.
Change the coefficient. And now what do we do?
Change the coefficient.
I don't accept that, but I know why you're saying it.
Check it again.
Check your work. You go back, you reset the whole question, and we'll go through and we check again. Golds on the left-hand side, 2 on the right, 2. Coppers on the left, 3 on the right, 1. 1's not correct. I have to make that a 3, so I can put a 3 there. Now I can do sulfate. Sulfate's on the left. 3 on the right,
Now I see why you check her.
3. Now what do I do? You check it again. And you check it again, and you check it again.
Until it
Okay?
happens.
Okay? Until you've cycled through several times and you haven't changed a single number. Okay? Or you check it again and you keep changing things. If you've checked it again and you're at probably 4 or 5 checks and every single time you've changed a number, what does that mean?
Probably done something wrong.
You did something wrong. The something that you did wrong is you did not predict your products correctly. Go back and check those formulas and make sure they're correct. That's the mistake you made. All the way at the very, very beginning. Yes?
Just to be sure, the reason the gold doesn't have a charge is because of itself, right?
Gold does not have a charge because it is by itself. Yes. Okay? It's in its elemental state of a solid. Okay? So we now have a balanced equation. So the question I could ask, sum of the coefficients. 5 and 4, we'd get 9. Decent. Okay. Last question. Does it happen? Does this reaction occur? To answer that, we officially need to look at the activity series. Did I give you an activity series here? No, that was mean and evil of me. Okay? So let's try and come up with a way to reason through this. Do we know something about copper? Do we know something about gold? They're both metals. They both had charges change. Keep going. They're both metals. They do conduct, both of them conduct electricity. Gold actually conducts it better than copper. Why do we not use gold in all of our pipes then, or all of our electrical wires? Because it conducts electricity better than copper. It's really expensive. Why is gold expensive? It's not all that rare either. Why is it hard to get? What is our form of currency? Everybody pulls out a dollar bill. It's a dollar bill, right? No. What is our form of currency? That dollar bill only has value because of Fort Knox. What is in Fort Knox?
Gold.
Gold. Gold is currency in the human world. When we look at dollar bills and coins and all of that, we're saying they hold value based off of the gold we have in reserve. The instant we lose the gold, what happens to our paper? Completely and utterly worthless. Okay? So what is happening? It's actually worth less than the paper it was printed on, because that paper is expensive. Okay? So why would we pick gold as our standard of currency? Copper is shiny.
It's been around. It's shinier.
Copper's been around for at least as long as gold, if not longer. No, we could run something with density, but no.
Someone liked it better. Someone liked it better.
Have you seen copper out in the world?
Yes.
Yeah, what happens to copper? What color is it?
Brown.
Copper is an orange, shiny color, right? But it turns green. Why is it turning green?
Oxidation.
It's reacting. It's doing a chemical reaction. So we have copper that's nice and pure and clean. Here's our currency. And then what does it do over time? It turns into something else, which could dissolve in water. So let's push that to the extreme. Let's say we've picked one of the group 1 metals. You guys seen the group 1 metals get thrown into water? Yeah, usually big explosion and they dissolve and all that fun stuff. Let's say the U.S. decided to base its currency off of lithium. Guess what our terrorists come through to do to Fort Knox?
They throw them.
They run through with super soakers and water balloons, and they destroy our entire economy because the water hits the lithium and it's no longer solid lithium. It turns into ions, and then it dissolves in the water, and then it goes down the drains and out into the river and kills all sorts of things because it's bad. Soaks into the ground, and we now no longer have a currency. Instead, when our enemies come in with super soakers into Fort Knox and start spraying the gold with water, what happens? Nothing. Well, nothing happens to the gold. And arguably the people shooting with super soakers, probably nothing happens to them too, because everybody's like, you're just an idiot. Okay? Why did we pick gold? It doesn't react. It is an insanely stable species. Copper, on the other hand, we've seen it. Right? Statue of Liberty, isn't the Statue of Liberty made of gold?
Statue of Liberty's on
Or copper? Yeah, it's made out of copper, right? Okay?
Also the state.
And that's not that nice kind of shiny orange color, right? It's that weird greeny blue color. What's happening? It's dissolving. It's changing its state. Right? We don't want our currency based on that. So when we look at this chemical reaction, we know something about gold. We know something about copper. Copper is reacted. Gold is not. Right? Given the choice, would you get up out of bed or just kind of chill and relax? Chill and relax. Okay. There were obligations that forced you out of bed. That took energy. Chemistry's doing the same thing. Does gold want to react with anything?
No.
No.
It's lazy.
Copper, in comparison to gold, would. We take a look at our reaction. Gold on the left-hand side, copper on the right, all by itself. Which of those states is more better? That was a horrible phrasing. Gold is happier to be by itself. Where's gold happy to be by itself? On the left-hand side of the equation, which means does this reaction progress forward? No. Okay. We can understand something about the activity. We can start to predict whether the reactions occur. That's one of the powers behind these things. Okay. Our combination reactions, I don't really want to talk about. There's a whole bunch of balancing stuff and nomenclature practice, but we don't need that. Arguably we do, but that's beside the point. Decomposition reactions, we could go through and do more practice with our decomposition. Okay? Again, it's just practice. Nomenclature and all of that and balancing equations. You're not expected to predict the products of decomposition or a combination. You're expected to just recognize what they are. Our single replacement is where our predictions are needed, and this is what we just talked about. This comes back to our activity series. Gold is at the bottom of our list for activity. It is the least active metal. Lithium is the most active, which means given the choice between lithium and gold, lithium would rather be in a compound than gold. I can use that to predict my reaction, okay, or to decide if it occurs. You should still predict what your products would be if it occurred, But then what you're deciding is, does the arrow in between actually make sense? Google it. You Google a video, you'll be fine. Okay, so let's take a look at, let's go ahead and do this one real quickly. Silver chloride plus what? Aluminum. The aluminum is coming out in a full single replacement, which means its phase is a solid. Okay. Silver chloride, if we're just assuming our equation, comes out as aqueous. It's really coming out as something else, but let's ignore that. Okay. We now have our equation set up. Did we predict our products correctly? You're shaking your head no. Why? That's a different question. She said it's not balanced, so you did it wrong. You didn't say they did it wrong, but I added that. Okay. Did we predict the products correctly? Before we can attempt to balance, we have to make sure our products are correct. Aluminum is supposed to come out all by itself. The real question is that silver chloride. And maybe this is where you were going. You saw 3 there and said, well, you didn't draw the 3 over here. Okay. So it's not balanced. That's a separate question from predicting the products. How do I determine if I've predicted the products correctly? Metal and non-metal, I had that. What's the next thing I need to look for? Charge. What is the charge on silver? Plus 1. How do we know this charge on silver is a plus 1?
Memorize.
Unfortunately, it's one that you just have to memorize, and you just happen to be off by 1. Cadmium and zinc are plus 2. Silver is a plus 1. What is the charge on chloride? -1. Is my formula correct? Yes. Now that my formula is correct, now I can balance the equation. It's not balanced. Thank you for pointing that out. How do we fix that? Okay, I need 3 chlorides to balance that out, which then means I have 3 silvers. 3 silvers. The aluminum's balanced. Yes, I did that very quickly. You should be that fast. Should this reaction occur? So this comes back to our activity series. Here's silver at the bottom. And there's aluminum part way up. Aluminum is more active than silver. Okay. If aluminum is more active than silver, it prefers to be in a compound. Where is aluminum in a compound in our equation?
On the left.
On the left-hand side, the reactant side. That's where aluminum's happy. If it is happy there, is it going to change states? No, which means the reaction doesn't occur. Ooh, that's interesting. I actually spun that differently than we had just talked about. Because previously I talked about the metal. The more active, the more likely it's a compound. The less active, the more likely it's not. It's by itself. Silver is less active than aluminum, meaning it should be by itself. Where in our equation is silver by itself?
On the left.
On the left-hand side. Either way we evaluate it, we get the exact same answer. This reaction does not occur. Okay? You have to be able to answer at each of those stages. Okay? The reason these equate, or the next big thing, I will give you an activity series. Yeah, it's okay if you pack up, just pack up quietly, please. I will give you an activity series on the exam, a condensed one, because I don't want that whole thing there. Okay, so that will show up. The important part is not this slide, but realizing that what these are is a step into oxidation and reduction. Okay, which is the video you watched in theory this weekend. Okay, and that is where we will start Wednesday. Okay, what I would recommend you do is you go back and take a look at any of these single replacement reactions and apply the oxidation state concept that was addressed in the video back to these to see what's going on. And what you should notice is that it fits nicely. With that,